Today we are going to be talking about exponential functions, and we're skipping over section 5.3, which is all about finding inverse functions. So we've already dealt with that. It's where you switch the y and the x, right, and then you solve, and you get the inverse function. And so anyway, what we're doing today is looking at exponential functions, and the cool thing is the natural exponential function is the inverse function of the natural logarithmic function, f of x equals ln of x. So we look at this notation here. This is f to the negative 1, which really just means f inverse of x equals e to the x. So what it's saying is the inverse of natural log is e to the x. So what we know about inverse functions is they undo each other. All right? So if we take the natural log of e to the x, that really just equals x. It's like doing 1/2 times 2 equals 1. Okay? The same thing, natural log of e is just going to equal whatever exponent that is. Another way you can look at this is e to the natural log of x is going to equal x. So here are the graphs. Here's natural log of x, and here is e to the x. Do you see the inverse relationship there? Okay. So we know if we switch the x's and the y's, we're supposed to get the inverse function. And so geometrically speaking, if we reflected natural log over the line y equals x, we get its inverse, which is e to the x. Okay? So here is your exponential function. Some other properties. The power or your exponential rules still apply when you're talking about e. So e to the a times e to the b equals e to the a plus b. And then e to the a over e to the b equals e to the a minus b. So in our first two examples, we just want to solve the exponential equations for x. All right. So what we want to do is take the natural log of both sides, because the natural log undoes e. Okay, so we have natural log of 7 equals natural log of e to the x plus 1. Natural log of e, it undoes itself. It equals whatever that exponent is. So here we have natural log of 7 equals x plus 1. And then to solve, we would just subtract 1. Oops. That was a nice words with friends sound there.
So do you play it too then?
I do.
Do you win?
I do. Okay, so once you get it to this form, you just plug it in your calculator. And we get 9.946. Okay. So in our second example here, we have the natural log of 2x minus 3 equals 5. So how do we undo the natural log function? Well, it's not times e.
The power of e?
We do this. E to the power of natural log 2x minus 3 equals e to the power of 5. Okay. So if we look at this property right here, e to the ln of x equals x. So if we do e to the ln of 2x minus 3, this just equals 2x minus 3. It still equals e to the 5. And we solve from here, add 3, divide by 2. Okay, and you can see the e button. What do you know? It's conveniently located right by the natural log button. I wonder why, because they're inverses. And you can see here the set of inverses, x squared, the inverse is square root. Here log 10 to the x, here ln e to the x. So we're just going to go e to the 5th power plus 3, and then divided by 2, 75.7.
707.
So that'd be
Yeah, so 75.707. Okay. Now what we're going to do is we're going to explore the derivative of the e function, and we're going to use our y equals again. So do you still have it with ln's in here from last time? Remember, this is what we did last time? No?
we didn't do that. Yeah.
Yeah, remember the derivative.
Oh yeah, I have Ellen.
Who's signed over still?
This is the limit definition.
I have 5/2 though.
So remember, it's f of x plus delta x minus f of x over delta x, and it's the limit as delta x goes to 0. That's how to find the derivative. So I still had my natural log in here, but let's just change it to e to the x. Okay, so we're going to graph our original function e to the x, and then we're going to graph the derivative. And remember, we're just going to let delta x equal 0.001 because it's small enough to give us an accurate kind of representation. You can do 0.000001, whatever, but this is going to be good enough.
Minus the x as well.
Yes. Okay, so there is our limit definition for the derivative. We're going to graph both of these at the same time. What do you mean?
Oh, and that. What if you change your function to the e's?
I just changed my function to the e.
Is that the opposite? Can you do that?
No, we're finding the derivative of e.
Okay.
We're finding the derivative of e to the x.
Okay.
Okay, so go ahead and push graph. There's our e to the x function.
Wow, it's the same thing.
Yeah, why did we only get one? Because they're the same. So if you push trace, there's the e to the x function, and then we push down, there's the derivative of e to the x. Let's just kind of go over here.
How can they be the same?
And you can see they're off just very slightly. But that's because we used 0.001 and we didn't use going to 0. Okay? So what that means is the derivative of e to the x is just e to the x. Think about that in terms of slope. That means the slope of this function is the y value of that function. Always. So if you go over here, the slope is whatever y value this is. And it's always the same going all the way up the entire graph. Okay, so if the derivative of e to the x is e to the x, and we know derivative is slope, what that means is the slope of the function e to the x is the y value of the function e to the x. So its slope equals how high it is. Kind of crazy. Anyway, let's...
Why does the number 2 point whatever make that happen?
It's an amazing number.
Did they actually solve it?
Mm-hmm. So let's do some differentiation here. So we want the derivative of e to the 2x minus 1. Now, of course, the chain rule still applies here. So if we have e to the u, then we have e to the u times du dx. So what we're going to do is let u equal 2x minus 1. And then we need to find du, which is 2 dx. And so we know the derivative here is going to be 2 e to the 2x minus 1. That's the answer.
That's good stuff.
So it's the derivative of the exponent times exactly what it is. All right. So here for letter B, u equals negative 3 over x.
Oh, it must be negative.
Du is going to equal
Positive 3.
positive 3 over
And you don't work.
x squared.
Because you're stepping it down.
Okay. So negative 1 goes down 1 to negative 2. Yeah, which makes it look like it goes up in the denominator. So our final answer here is going to be 3 e to the negative 3x over x squared.
Why is the negative go there?
Because the exponent on x, this is like negative 3x to the negative 1. And so when you do the power rule, negative 1 times negative 1 makes it positive. And then negative 1 goes down by 1 to negative 2. And then it moves it back under the denominator. Okay. So if you have trouble with that, rewrite it like this. And then maybe you can see it a little bit easier.
Oh, yeah.
So remember the
Yeah.
negative 1 here, and then this goes down 1.
Yeah.
So really I have 3x to the negative 2.
2, 2.
Okay. So kind of gives you some insight for our next one. For C, we're going to let u equal the square root of x squared plus 1. And we're going to rewrite that to the 1/2 just to make it easier. And then we're going to find the derivative. So notice we're going to have to use the chain rule. So we see all this stuff inside raised to the 1/2. So the power rule says we get 1/2 times all that inside stuff to the negative 1/2 times the derivative of all the inside stuff, 2x. Okay. So you can see 1/2 times 2 is going to cancel. And then x squared plus 1 to the negative 1/2 will just go under into the denominator. Exactly. So x over, and we can change this back into a square root then.
You just times all that by e to the power of 2.
Mm-hmm.
Okay.
All right. So now we just multiply the two together. So this is going to be x e to the square root of x squared plus 1 over the square root of x squared plus 1.
That's the derivative of f e to the power of whatever?
That's the derivative here, yep. All right. In letter D, now you can see a combination composite function here. So we have x squared times e to the x. And so we're going to use the product rule.
Can it never be easy?
And this is super easy because notice it's just e to the x,
Which turns into e to the x.
which turns into e to the x. So we're going to have the first function times the derivative of the second
Plus, right?
plus the derivative of the first function times the second function.
So it's just
And there you go. You're done. You could factor out your e to the x,
Or we could not.
but we don't
we
need to.
could pull out of
E to the x.
no, we could pull out
X e to the x.
X, yeah.
Yes, we could. That would be lovely.
Let's do it.
So what would it be, x plus 2?
Yep.
Yeah. So there are, various forms that we might see this in.
I like number 8.
letter
Right.
Okay. Let's move to the next one. We have e to the x ln x. So what we've been doing this whole time is letting that exponent equal u. And it's no different here. So now we have the derivative of x ln x. X times 1 over x, because it's the first function times the derivative of the second. And then the derivative of the first function, which is 1, times ln x. Exactly.
That was a time for
That's product rule also.
Natural log of x, the derivative is 1 over x.
Yes.
What's the integral? Natural log of the absolute value of x?
Mm-hmm.
Then now we just multiply that.
Now we just multiply it. So we have 1 plus ln x times e to the x ln x.
That's why there's
Needs to be improved. Over here.
Okay.
Oh, for these, do we just add the exponents?
Right here.
Yeah, like an e.
What do you think? Do we have that rule for our exponents? What's the operation between the two?
Oh, they have to be multiplied.
Have to be multiplied. So addition, can't add those. That would be easy if it was, but no can do. So if we're looking here, we're going to use the power rule with the chain rule.
Powerful chain rule.
So y prime, it's going to be 2 times all of our inside stuff. And we're going to lower 2 down to 1.
e to the negative x. Does that stay the same?
Okay, so e to the negative x, we would let u be negative x, which is du means negative 1. Okay, so it's negative e to the negative x.
E to the x.
Okay, everybody with me on finding the derivative of e to the negative x?
No, why does it say negative x?
Okay, so we let u be negative x, du would be negative 1. So there's du. Okay, and then the derivative of e to the x is just e to the x. And now we'll just kind of clean this up a little bit. We got 2 e to the negative x plus e to the x. And we'll just rewrite this with the positive one first.
Now, would we be able to add those exponents to